Hello. How's it going? Everyone hear me at the back? Yes, fantastic, cool. So my name's Richard, and I'm going to be talking a little bit today about some more kind of like deep dive performance issues, things which are perhaps stuff people don't normally do. So I guess the motivation for this is that a lot of people talk about performance in their systems as though they were like some kind of amazing F1 car, and the reality is things look a little bit more like this, more like a kind of 3D animation of a toy kit car. So, just a brief overview of the talk structure. I'm going to kind of motivate some of the low-level details we're going to talk about. Some people I know always refer to this kind of stuff as low-level rubbish, which is not necessarily my perspective, but an interesting one. And I'm just going to go through a few different things that you can think about in terms of writing software in a way that works in harmony with your hardware. So we're going to talk a little bit about branch prediction, different memory access values and caching, and then we're going to talk about storage as well. And then hopefully draw a few of these threads together in some kind of conclusion. So, I read this kind of high scalability blog from time to time, which is quite interesting because you see people giving kind of war stories or information about how their systems are performing and talking about what they've achieved. And some of it's quite interesting, but sometimes you get things like this, which are like, we were doing 80 messages per 60 messages per second, and we had some Elasticsearch servers, and we were using AWS, and we had some HA proxy, and all these kind of different things. And they were talking all about the technology they were using, and they were talking about these kind of throughput numbers. And then when you kind of divide the time period through and the machines, you realize they're processing like 0.7 messages per server per second, which doesn't sound that great, really. But I'm not saying necessarily these people were doing it wrong or had problems or anything like that. I'm just pointing out that this is a kind of very weird discussion to be having, to frame it in terms of the technologies. When you see people kind of talking there, it always makes me cringe a bit. Whereas I'd like to have more information on principles and methodology and what you can measure and what you can get there. And I guess it comes down to this. A really good quote the other week I saw on Twitter, or maybe a month ago now, was, all we need is less hipsters and more geeks. And the previous example was from a company called HipChat, which is basically like IRC for hipsters. So I guess there's a different series of talks you can give about performance, and some of them are like product solutions. So just use our library tool framework, everything's web scale, everything's amazing, right? And then there's this kind of architectural advocacy talks that you see as well. If you design this way, it'll magically scale and it'll magically work fine. And this is more a methodology and fundamentals talk. So I'm going to be talking a little bit more about how the hardware works, about how hardware and software interact together, and what you can measure and what you can think about when looking at these kind of things. So a bit of an alternative approach, but something which I certainly myself feels a little bit more natural. So some of the things I'm going to be talking about are very, very low-level things. They're quite hard to optimize, hard to access, and potentially quite time-consuming to get right. Which brings up the question, before we move on to them, of where do you actually want to do it? Well, you want to do it at a bottleneck, right? And this slide is a bottleneck, if nothing else. Apart from this guy, who seems to be driving off into the distance as though nothing had happened. And the other kind of thing you might want to think about is where in your application do you need to worry about these kind of performance issues, and where can you not worry about them? So I did some work recently on an open source message transport called Aaron, which has been released now, which is quite interesting. And the kind of core driver that Aaron has 3 threads to it. So, well, actually it's quite configurable, but default configuration has 3 threads. And there's one thread which is just sitting there, shoveling bytes from the network into some kind of buffer. And there's another thread that's sitting there, taking data from some buffer and shoveling it out onto the network. And these are threads which are absolutely living on the latency path for every message that goes through the system. If these are slow, everyone's going to have a bad time. Okay? There's another thread that's sitting there managing connections, opening, slowing, and kind of admin information, and a bunch of all sorts of little just tasks to keep things ticking over, you know? And the admin thread actually probably has most of the code ends up getting executed there. But it's also the thing which you potentially don't necessarily want it to be slow or necessarily impact the other threads, but as long as it's getting out of the way, there's no need to overly optimize or overly worry about that kind of thing. So when I'm talking about these kind of situations, I'm only really saying critical path where it's really important. And the unifying theme for the talk, I guess, is I've seen a lot of different information or bits and bobs here about how hardware works, and a lot of it's very useful when doing that kind of low-level optimization side of things, or that you've already got through all your dumb bottlenecks, what should you look at next? But it's quite a diverse set of different things, and I think one of the things which goes throughout these kind of aspects, throughout these kind of hardware, is try and do simple, predictable things which your hardware finds it very easy to understand and very, very easy to deal with. The other thing is, before we go any further, there are a lot of performance problems which won't be related to what I'm doing today. I'm not claiming to be a prophet or solve any of your problems, and unlike Scientology, you don't need to give me any money on a regular basis. So in each of these cases, I've put in an optimization omen, which is the evil kid, which is something you can measure, and that measurement will tell you this is really a problem, this is something you can understand. Okay? So, let's talk about branch prediction. So, all CPUs do 4 things. What are those 4 things? Question to the audience. Fetch. Anyone else? We got fetch. Execute an instruction. Write some data back to main memory, yeah, and obviously decode the instruction that you fetched. Now, after a while, CPU manufacturers realized they could do these things in a pipeline. So whilst your first instruction, once you've hit a few come through, you can have one instruction being fetched, another decoded, another executed, and something else being written back at the end. And that's kind of pipeline CPU architectures. And if you think your CPU at this point is sounding a lot like Sisyphus, who pushed a rock up a hill forever, that's a perfectly reasonable thing. Your CPU is doing exactly the same thing, and it needs to be driven exactly as hard as Sisyphus. So, having decided we can pipeline things, we can do super pipelined and superscalar architectures. So superscalar architectures look at executing multiple instructions at the same time, and super pipelined architectures end up being very long pipelines, so split these operations down into smaller micro instructions and smaller bits and bobs, and then they can pipeline them more extensively. Now, the problem you hit with this architecture, with this approach, is what do you do about branches? So whenever you've got so here's some simple Java code, and you've got an if statement in the middle of the method, and depending upon whether that statement's true or false, it might execute this bit of code, or it might execute this bit of code. Now, this poses a problem for that pipelined architecture, because you don't know what the next thing is to start fetching and decoding once you hit that branch, because you don't know whether it's the true branch or the false branch. So, branches themselves can potentially cause your CPU to stall by not knowing what to execute next. And stalls kill performance because your CPU is sitting there having a rest on your time. And you don't really want to do that. So, quick hands up. Can we eliminate branches at the CPU level? What do people think? Who thinks we can get rid of them entirely, just throw them away? Lack of enthusiasm for that option. Okay, so the strategy that modern CPUs end up doing is to predict branches and speculatively execute them. So there's some mechanism in play that says, are we going to go down the true branch or the false branch? And depending upon that, we're going to start prefetching the next instruction. Simple strategies which people use and which still end up being employed in a lot of ways today are static prediction strategies. So static prediction strategies don't take into account any kind of runtime information when making this prediction decision. Now, the static prediction strategy which most CPUs, especially Intel CPUs, undertake when they have no further information about this branch is if you've got a forward branch, it defaults to not being taken, and if you've got a backward branch, it defaults to being taken. And the reason why you might want to do that is because you might want to have back edges in loops which tend to be taken repeatedly, because most loops go around more than 0 times. And with forward branches, frequently end up being less use cases on if statements. Now, a lot of the time it looks like you might have runtime information, but because that runtime information is really finite and quite limited in some respects, you might not have information which you think you have available to you. So static prediction strategies are still valuable. Now, how does your CPU encounter this kind of prediction strategy? Well, it's very easy to see when you're looking at the assembly code. So we're taking the value of x, we're moving it into the AX register, we're comparing that with 0, which is that branch. Then we're jumping, if it's not 0, to the end. Otherwise, we're moving 1 into the AX. Otherwise, we're incrementing it, and then we're going to store EX back in X. So here's a conditional branch at this point in time, and it's pretty easy for your CPU to see that conditional branch when it's executing code and make a runtime decision based upon it. So in the Pentium 4, Intel added static hints. So the idea was you could give a hint to your CPU about whether a branch was going to be taken or not, and depending upon that hint, the CPU would go ahead and take it. So these _emit instructions are kind of magic instructions that don't really do anything, but just offer hints to your CPU. And 3E is taken and 2E is not taken. The interesting thing about these kind of hints is that actually Intel said, well, you shouldn't use them, just flip the branch around. Things like this are actually not very useful. After a while, obviously, CPU manufacturers looked at dynamic prediction strategies. So dynamic prediction strategies record some history or information about the program as it executes, and then they use that historical information in order to predict the future. A bit like clairvoyance, but probably more effective. So the way CPUs do this is they have what's known as a branch target buffer. So a branch target buffer is whenever your CPU is hitting a branch, you keep a log of what's happened, and each entry in this log corresponds to a previous record about a branch. It also stores the program counter address, so it knows when it comes back to that point in time in your program how to look up that instruction. Branch target buffers are finite, so that means at some point in time, you can't have like an infinite history, obviously, you can be only have a finite amount of space for this kind of stuff. So you might hit a point where even if you've seen it before, even if you have a good record of information about what happened to that program counter address, your static prediction strategy can still end up being used because it's kind of gone around far enough to not have remembered that within the finite history. Now, there are multiple different varieties of strategies for branch prediction that CPUs undertake and use, and some of them are referred to as local strategies, and some of them are referred to as global strategies. So local strategies try and record branches for a given instruction or a given program location, and global BTBs record over the whole program and actually end up being much more effective at tying together the history of branches. So modern branch prediction strategies have the ability to say things like, well, I kind of know what the previous instruction was, so what's happening here? So unlike, beer and food and things, local's not necessarily better in this case. Some CPUs have loop-specific branch prediction strategies. So they have a specialized predictor when they see a cycle happening after a certain number of times, and also information storing about functions. It's interesting that, again, these seem to be things which modern CPU manufacturers have just moved away from in favor of what's known as an n-level adaptive predictor. So an n-level adaptive predictor in the branch target buffer stores records that say, well, actually, it corresponds to this previous branch having been taken as the previous instruction and things like that. And that lets you account for kind of patterns like nested if statements, where one if statement that's nested within it might be predictable if you know the result of a surrounding if statement, but not otherwise. So when you're coming to look at this kind of information, the thing which I'm aware of, and the thing which I'm aware of most effectively for recording information about branch prediction strategies, is known as performance event counters. Quick hands up who's heard of performance event counters, or MSRs? Some people? Okay. So performance event counters are a special type of register that sits on your CPU and counts like an architectural event about the CPU. So it might be a branch prediction hit, might be a mispredict, it might be a cache hit or miss, all sorts of different things. And these are, as I say, model-specific registers. So that means they're not standardized in like x86 or anything like that. They are specific to your CPU and specific to your architecture. And they can differ quite widely between different manufacturers and different variants of CPUs. It's possible to configure these performance event counters and say, store the value of this specific thing, and then you're able to measure and monitor that kind of thing. There's a bunch of existing tooling and profilers which will let you measure these performance event counters, such as Perf on Linux is just an open source free one. There's things like vTune, AMD Code Analyst, or Oracle Performance Studio. There's all sorts of things which are pay-for tools, and some of those pay-for tools also give you tie back into your source code, so you can understand what was actually being executed rather than having to do the isolation to micro benchmarks yourself. So let's just a quick look at Perf and see what happens when we run it. So suppose we've got some Java program like this which makes up a block of data. So the making of the block of data basically puts a bunch of random numbers into an integer array, and they're either 0 or 1. And then, interestingly, you loop over the array and do it quite a lot, and you, depending upon whether the value in the array is 0 or 1, you can either branch or not. Now, that's the kind of thing which you'd think would probably do really badly, right? Because it's the kind of thing where you think there's a lot of randomness involved, but actually, your CPU ends up doing a really great job of understanding what's going on. So if we just look at what's going on here, we can see the branch miss ratio only ends up being 0.17% of all misses. And that only took 1 second. But it's possible to make, very, very small changes to your application. So here's one that will confuse it, involving adding in the current time and stuff. And that's just a small change into that if statement. And then if we recompile that, and all pray to the demo gods, we'll see, glorious. Well, it's obviously taking a lot longer than the first run of the application, and we can see up here we've had a massive increase in branch misses, a massive increase, a massive worsening of your CPU to the ability to predict the program. And we're also worth noting that this application's ended up running like 5 to 6 times slower. I mean, it's a very, very small micro benchmark. I'm not claiming that necessarily is reflective of any real-world program, but it's just an interesting example of how much of an impact such a small change can have in these kind of isolated situations. So a quick summary on this section. Modern CPUs end up being super pipeline and super scalar. Branches can cause stalls, And it's possible to optimize your code just by simplifying these situations. And it's also worth noting that branching in terms of what your application is doing is not just if statements within your program. It can also be things which your object-oriented systems dispatch ends up doing. So a lot of polymorphic calls end up resulting in some kind of branch as well. Okay? So let's talk about memory access and memory times. So the ongoing problem that a lot of people have in terms of their performance of their system is that processors, this is a Sandy Bridge I think, end up being very fast, not only very fast, but increasing in performance all the time. On the other hand, the bus between your CPU main memory and your memory has only been increasing by an average of 9% a year over the last decade, which is significantly slower. So whilst these are both exponential growth curves, there's such a difference in the rate that the difference is also ending up being an exponentially increasing difference. Now, the solution to these kind of issues used to be the idea of a CPU cache. So when a CPU core demands some data or wants to write back data, it looks at its cache. If the data is present, then there's a hit, and the data gets returned to the register from the cache. Otherwise, it ends up round-tripping to main memory. And the idea is that so firstly, fast memory ends up being quite expensive, whereas a small amount is affordable. And also, if you end up with a situation where you need lots and lots of memory that needs to run very fast, you massively increase your thermal dissipation overhead. So it's very hard to cool these things, which is a problem. Taking the idea of a cache further, modern CPUs end up with multi-layer caches. Okay? So you end up with L1 cache being shared between the two hyper-threaded cores on a single chip and on a single core. So this is Sandy Bridge, but also applies to like Ivy Bridge, Haswell, pretty much all modern Intel chips. And then L2 is unique to that physical core, but shared between those hyper-threaded cores and shared between data and instruction caches. There's a shared L3 cache that goes across all the different cores on a socket. So how bad's a miss? These latency numbers were measured on my old laptop. Obviously, it will differ quite a bit depending on architecture, system, all sorts of things. But round-tripping latency from a register to an L1 cache was about 3 clock cycles. L2 was 9, L3 is 21, and obviously there's a huge, huge difference up to main memory, and that's quite hard to measure anyway. So it's really, really bad is the answer. To minimize the overhead of the latency of loading data from main memory, CPUs act a lot like Sylvester the cat in the sense that they eagerly perform their job of loading data from main memory. There's a bunch of different strategies available for doing this prefetching operation. Some of them are to prefetch cache lines which are adjacent to the one that you're accessing, and there's also streaming prefetchers which start looking at pulling in data further and further ahead when you see regular patterns. Now, you can't tell your CPU in any way, hey, go prefetch this data, this is the thing I want to worry about. You have to arrange your data in memory so that these accesses can be made predictable. And the overall term for arranging data in memory in this way is locality of reference. And locality of reference comes in kind of two big forms. So there's temporal locality, and the idea there is that you're repeatedly referring to some data, the same data, in a short time span, so it's cached and you're looking back over it. And the other idea is spatial locality. So that's referring to data that's close in together in memory, because then it's more likely to be cached. Sequential locality is a special case of spatial locality where you're accessing data that is linearly laid out in memory. So it's a special case of spatial locality. General principles in terms of this is, partly using smaller data types or data types that involve less pointer chasing or indirection, and avoiding these kind of big holes in your data where you end up looking randomly all over the place, making accesses as linear as possible in order to take advantage of that sequential locality. So let's talk about primitive arrays in Java for a sec. So primitive arrays end up being laid out sequentially in memory. So if you have a loop like this that's just iterating over an array and incrementing every value, it'll have an incredibly predictable access pattern. Now suppose you start looking at holes in this data. So there's some skip value that's going through, and as you increase that skip value, you need to start, it's harder to predict what the next value is. So this is just the output of a cache profiler and looking at the different size of skipping holes. Now this is a miss ratio, so the higher you are up, the worse the misses are. So there's like 100% at the top, so that's really bad, and the bottom's really good. This is the situation when I was running the benchmark with a skip of 1, that with 2, 3, and 4. And you can see that the miss rate on the L2 cache is flying through the roof very, very reliably following the change in those skips. And you'll see there's an impact on the L3 cache, which also starts creeping up as well. So the thing to bear in mind with multi-dimensional arrays in Java is that unlike C, multi-dimensional arrays in Java are arrays of pointers to other arrays. So this means that it's very much harder to get that kind of predictable access pattern and linear memory layout with multi-dimensional arrays. So in order to work around this problem, some people realign their array accesses. So they'll use a very large array of the size of, the number of rows times the number of columns, and then they'll do some kind of offsetting to this. So, the total number of rows times your current column plus your current row, and that gets you to your current index. The thing that's worth bearing in mind with this kind of situation is that you need to make sure that you've aligned your memory in the same way that you're planning on iterating over it. So here is a situation where you put column value by column value, and you end up with a really, really bad miss because you end up striding the length of your column every time. Whereas here's a situation where you're striding the right way, and you end up with good locality by comparison. These are numbers of the different variations of the benchmark in a cache profiler again. Now, it's worth noting the difference, this is measured on that laptop, of the difference between fully random access over memory, so that's access to arbitrary offsets in memory where you don't know where they are, versus sequential access. And you'll see at the L1 side of things, once things are in L1, it's pretty much the same because there's no cache level impact from this. Once you start hitting L2, it's already multiple times slower, and when you hit main memory, you end up being increasing your memory latency access by 10-fold. So any situation where you've allocated an object and it could be somewhere arbitrarily in memory, and you don't know how many of them are, and they're all over the place, and you end up doing pointer chasing to find that object, so you can call it, ends up with a significantly larger overhead in terms of your memory access. Good data layout principles can involve using primitive collections. So there's a bunch of things which are basically collection variants where they've written out the collection or code-genned it for all of the different primitive types. So GNU Trove is one of the oldest one. GS collections and FastUtil and HPPC are other ones. They might all offer some other different variations or other interesting features for you. Arrays generally end up being better than linked lists because arrays at least have a predictable spine, whereas linked lists you end up with that random access pointer chasing every time you're iterating over it. And the same thing with a hash table versus a search tree. You end up with that kind of random access pointer chasing as you go down the tree. And it's worth avoiding bloating your code too much, which might involve, say, manual loop unrolling and things. It's also possible to do a bunch of custom data structures, which are generally designed to be very cache-friendly. So Judy arrays are a kind of like associative array, like a map-type data structure, which is designed to be more cache-friendly. KD trees are like a way of splitting up your data in like a binary space partitioning, but for multiple dimensions, not just binary. And Z-order curves are basically the thing I showed you earlier where you had the rows and the columns and you were doing that, mapping 2 dimensions into 1. Z-order curves are a generalization of that to multiple dimensions, where you kind of stripe across your data in a big Z. I won't go into how these work, but they're worth having a look at. The other thing that's not so great in Java is that we end up with a load of these heap allocated objects. When you have an array of those objects, you already have an array of pointers to those objects, and they may be laid out arbitrarily elsewhere in memory. So when you're iterating over your array of foos, you getting a pointer to a foo, and then an object may have other values coming off it. And there's a huge amount of pointer chasing that goes on there, and then you're back into the random access territory. It is a bit of a Java weakness. Hopefully a few people are going to help improve this situation and give us better options in future for solving these kind of problems, because it makes the location of objects in memory really hard to guarantee. Your garbage collector may well copy objects around the heap, or it may move them around within a heap space. So even if you get things allocated and laid out in order when you allocate them, there's no guarantee that they will be by the time they get promoted. Again, performance event counters are things that let you monitor and measure in this space, just as with the branch prediction side of things. You can measure the cache hit and miss rates at different levels of the cache, and then you can start looking at putting together ratios which might be more informative. It's worth noting that you want to actually correlate this with the idea that you've had some kind of stall, so you can figure out when you're stalling by measuring something called your instruction retirement rate. So that's the number of instructions that your CPU actually gets through within a period of time, and establish that it is actually being stalled, and then correlate it back to one of these underlying causes. There's a few people who've got proposals or things moving forward about offering more control over object layout. So one of the ones that's more interesting on GitHub is the Object Layout project by Gil Tenney and Martin Thompson, which tries to give you the idea of an array of objects, and all of those objects are laid out sequentially in memory. If you're in an off-heap world, there's a bunch of projects like Java Chronicle or the JC tools, which give you data structures which are built off-heap and manage the memory for you. It's also possible to use one of these modern serialization libraries like SBE, cap, and P, or flat buffers, which basically don't serialize data by copying. They just read and write out of a buffer, and then they also give you a potential for object layout control. Presumably in a future version of Java, there will be some value type situation which might help with some of these problems as well. So, in summary, cache misses cause stalls, stalls kill performance. You can measure how much of an impact this is through performance event counters, and there's a bunch of common techniques for optimizing code, mainly around making those accesses more predictable and putting data closer together in memory. Okay? Let's talk a little bit about storage. So, quick hands up. Who uses hard disks and their production servers? Who uses SSDs? A few people. Who doesn't know what they're using? Quite a lot of people. Please know what you're using. Yeah, hard disks are still quite commonly used persistent storage mechanism, or a spinning rust as some people like to refer to them, and they have a head which is doing some kind of read and write off a disk. Most modern hard disks end up being what's known as constant angular velocity, which means the rotations per minute that your disk is doing stays constant. And sector sizes differ between devices. So I'm going to mention a few things about sectors in a minute, but originally a lot of sectors were like 512 bytes in size, and then people came along and made all the sectors a load bigger. A simple model for understanding how these things work is a variant of constant angular velocity called zone constant angular velocity, or a zone bit recording, you might refer to it as. And in this situation, your disk ends up being split up into a bunch of little zones, each of which has a sector in. And when your computer wants to read that sector out of the disk, it needs to do a bunch of it. It's not an atomic operation, it has a bunch of different components. So firstly, it takes some time for your disk to process the command that says, hey, go read this data. Then it takes some period of time for your disk to actually seek around to get to the right point. And there's also the rotational speed latency. So that's the point in time it takes for your head to move to the right point on the disk. There's also sequential transfer time, which is once you've actually got there, you can start reading things out one after another. Now, one of the interesting implications of a zone bit recording, you can try this out on your own hard disk by taking a blank disk and starting to write and read from it, is that transfers end up being faster at the edge than at the center. Another more interesting aspect of zone bit recording is the implication that, again, sequential reads and writes are much more performant than seeking and randomly reading. When you have very small values of data, like a sector here or a sector there, the seek and rotational times come to dominate the value of time that actually takes you to read or write from the disk. And random writes of 4 kilobytes can end up being like 300 times slower on modern disks than like this theoretical data transfer rate, which is what the manufacturer will be telling you that the disk can do. So that's quite a significant difference in performance. It's also worth thinking about, even if you've got an application where each thread individually has a sequential access pattern on the disk rather than a random access pattern, you might have an application where you've got way too many threads and you're ending up context switching between different threads, and that has a bad impact on these things as well because you're back into a random access pattern because each thread might be looking at a different part. So, the other thing to think about is disk fragmentation can cause unnecessary seeks by making things that look like they're sequentially laid out actually being much further away from being sequentially laid out. And it's worth noting that some file systems, I think X4 does this, hold back writes of disks of multiple sectors of data, and then they flush them down in one chunk. So you get these sectors all batched up in a buffer, and then they get written down sequentially. The fantastically lovely open source software BitTorrent, which you should only use ever for downloading things which you have legal access to, has a fantastic approach to this problem, which is when you see it try to download a large file, it'll pre-allocate a huge chunk on disk in order to minimize the fragmentation of pulling in different chunks of that file. The other thing that's worth noting is the idea of sector misalignment. So you have sectors on your file system and you have sectors on your disk. And it's possible if your file system ends up offsetting its logical sectors from the physical sector, that you're going to end up with a really bad situation where you have to read or write 2 physical sectors for each logical sector. When a bunch of disk manufacturers extended the size of their physical disk sectors in the mid-2000s, and people were still using Windows XP, they would buy a new disk and find a huge slowdown in their disk I/O because they accidentally end up with this misalignment. Another thing is that you might have loads of software, for example databases, which have their own concept of a sector or a block within their software. So InnoDB is a storage engine within the MySQL database, and if you have a situation, so I'm saying Stripe here because it could be on a RAID array in this case, if it's a database server, and you have these database pages, which are the atomic unit at which the database is transferring data to and from the disk, and if these guys are nicely aligned with your stripes, you're going to get significantly better performance than if you end up with them being misaligned. So, obviously a load of people these days use SSDs. We saw that in the hands earlier. SSDs still have some of the same problems in the sense that it's still a situation where random access is slower than sequential access, though the distinction compared to disks is obviously much lower, but it's still something to think about in that situation. We talk about optimization omens. So here's just a simple command line tool called IOTop. That you can run on Linux servers. Obviously, there's a huge amount of different tooling that gives you access to this information. And IOTop will give you, for example, the percentage of time that a given application is spending performing I/O and the amount of data that's actually writing to disk. So if you see an application which is spending a lot of its time writing to disk, but not actually writing anywhere near its the amount of data that you think that your disk can perform in terms of read or write operations, then you might have a candidate for optimizing the disk access. So, summary on the disk front is that simple and sequential access patterns, again, beat random access and seeking all over the place. Fragmentation can make this random access significantly worse because it moves things around in the same way that the garbage collector was moving things around in our memory example. And the alignment of different sectors between different layers in your storage hierarchy, for example, a database, a file system, and a physical disk, can be important to ensure they're all neatly aligned. Let's just draw a few conclusions at this stage. So we showed some kind of theoretical slowdowns for a variety of these different situations. So we looked at large numbers of cycles for a stall for a branch prediction mispredict, and we showed a simple, although a little bit jury-rigged on my behalf, I'll admit, example application where it ended up being 5 times slower. We can have a situation where getting data, reading your data from or to an L1 cache ends up being 200 times faster than main memory, and again for sequential versus random access on disk you end up with a 300-fold change. Now these I'll admit are kind of theoretical max differences, but you might well find that by improving the situation you can get a significant speed up on those specific operations. Okay? So just a few of the overall themes which I talked about in this talk. Firstly, a focus on kind of principles and underlying mechanics over tooling, over saying, hey, just use this thing and it'll be web scale and everything will be magic. I talked a lot about these kind of optimization omens and things that you can measure, and I'm a big believer in measuring some data and understanding what's going on in an underlying system rather than making some unsubstantiated claim or guesswork. A lot of these things boil down to making things simpler in a sense, simpler for your underlying hardware in some cases, but on the branch prediction front, probably also simpler for you to read as well, which is lovely. A lot of the time people talk about doing some crazy magical thing to speed things up when maybe they could have just made some code a bit simpler. And again, a lot of these, when you start looking at optimizing software to work better with hardware, a lot of these situations have a memory access pattern situation where predictable access beats random access, where accessing things linearly or sequentially beats, seeking all over the place. There's a huge amount more information on the internet if you want to read more about this kind of stuff. There's a bunch of stuff about memory by Ulrich Drepper here, a bunch of CPU timing information, several people's blogs, and several mailing lists where interesting discussion happens on this kind of thing. I've reached the end of this talk at this point, and I hope you've enjoyed listening to it. And if anyone has any questions, now's a great time to ask them. Does anyone have a question? Shoot. Yeah. Well, that's an interesting question. The question was, if I understood it correctly, the idea that there was a lot more latency to reading blocks of memory rather than being worried about constricted by bandwidth, and you can get a significant speed up. But I think that advantage in a situation where you have a bunch of latency, but you have more bandwidth than you need, and you're trying to speed things up, is the kind of thing which your CPU cache prefetcher is designed to solve anyway. So I don't think, well, certainly to my knowledge or experience, there's been nothing else that you can do other than trying to let the cache prefetcher do its job as best it can, and then let it use that spare bandwidth in order to prefetch data accesses which it believes are predictably the next thing or soon to be the next thing. Does that make sense? Well, I think we're talking about accessing from main memory, right? So we're talking about aligning data in main memory more effectively so that you get better locality of reference, right? Was that not your question? Yes. Okay. Did you have another question? I think this guy in the front had a question, right?
No, we are introducing a lot of new paradigms which introduce a lot of indirection on code call. Has it an influence on performance?
So the question was, if you're moving to an alternative paradigm, does it have an influence on performance?
I mean, like, now we have lambdas, we have a lot of design pattern strategy, etc.
Yes. And the answer is yes, a lot of those things have potentially an impact on performance. But I wouldn't say that's not ever a situation where you want to kind of bastardize your code a bit to make it run faster in the absence of having any concrete evidence that there's a measurable improvement if you do so. The project in question which I was mentioning, which was a messaging system, actually was written in Java 8 and did make quite extensive use of lambdas. And in a lot of situations, lambda expressions perform very well. There are some places where you do seem to take a hit. So one of the situations we were in, because we were very concerned about latency in that situation, we were minimizing allocation, and there are some situations where you might think that you have a lambda expression which doesn't capture anything from its surrounding scope and can be made in a way that doesn't allocate it. But so far, not all of those optimizations have been worked out, and in some situations, it's not necessarily the case that it's a win in all cases. So, there's a lot of potential trade-offs on some of these optimizations which compiler writers are implementing. So that's something which just doing basic existing measurement like profiling, cache profiling, memory profiling, are things which will pick up those problems which you'll get from using different paradigms anyway. So to TLDR the answer, yes, they can make an impact. Don't make it worse, and measure what's actually going on, and then draw a conclusion about optimization based upon that measurement. Does that make sense? Are there any other questions? I think there's a guy in the middle there. Oh, okay. Oh, sorry. In that case, can I give a question to the guy on the left? Hello. Oh, thanks.
Can you give completely speculative hints about the libraries which promise to deliver the performance, but actually they don't deliver? And why?
So the question is, can I deliver completely speculative hints as to what libraries claim to deliver really good performance but don't? I think that's basically just on a route to me pissing massive amounts of people off, which I don't really want to do unless I have some data to back up that claim. So I'm not even necessarily claiming that some of those libraries or frameworks or tools that vendors pitch at you are necessarily slow. Some of them might be very slow. But the point is, I frequently see people having talks where they come along and say, just use X. X will make everything much better, solve all your problems, you'll be able to go home a lot earlier, you'll have no performance problems, everything will be great. And the reality that we all know is that that's not what that tool's going to do. It might, in some situations, provide you with a win, and it might, in some situations, provide you with a loss. And unless you measure whether that's a win or a loss, and try and understand the underlying behavior, there's no way of you being able to tell whether that's the case. So I'd rather not do speculative hints, is the TLDR to your question. Hi. Was the guy in the middle again? Yes. Oh, so you're saying, how can you reliably avoid being remapped to a different address? So I have no idea off the top of my head if there's any way of doing that, because I've never encountered a situation where the remapping has been a huge... When you're saying remapping, are you talking about remapping on disk sectors?
In the sense that, for example, LBA, the addressing does not guarantee the logical
Oh, I see what you mean. So what you're saying is you've got a logical block addressing in a file system, and that logical block addressing doesn't correspond to the disk. So yeah, so that is basically the same case as It's basically a situation like this, where you've got some, this is talking, where the heck's my pointer? This is talking about some physical sector and some logical sector. I know you're just asking about the generalized version of this question, basically, where you might have a logical sector and then another logical sector. And the answer is that if you've got kind of chains of things like that, in the same way, if you've got, say, database pages sitting on RAID stripes, which are then sitting on underlying addresses, is that you want to just make sure everything gets aligned right the way up from your physical sectors through an LVA right to the top. And yeah, so I think that will address the problem that you've asked. Does that make sense?
I think so, yes.
Okay. Do you have another question? Oh, sorry, guy there. Hello.
I'd like to attach to that question. Is there any practical tooling that helps you to find the correct sector addressing if you have a lot of remapping on the path to the storage?
Is there any practical tooling? You can figure out the sector size and striping value from the disk that you've bought and the RAID configuration, and you can figure out the sizing of the sectors on your file system from the configuration of the file system. So I think it's possible to just work that all out statically just by looking up information in the relevant manual pages, basically. Does that make sense? Yeah, the documentation might be lying to you. So again, as I say, correlating about the percentage of time you're doing I/O with whether you end up doing a lot of I/O is something that's worth thinking about. Beyond that, I'm not sure if there's any magical way of solving that problem that I'm aware of. Yeah, so I guess what I would say is look up the documentation, work it through in your mind, and then if you think the documentation is lying or there's something weird, you can probably chase it down with the manufacturer. But if there's a point at which your documentation is just lying to you, I'm not sure what you're going to do at that point. Okay? Hi.
The impact also of the file system can be quite huge. For example, when you've got a journaling file system, you've got 3 writes each time you sync to disk. One to write first the journal, then to write the active data, and then finally update the journal. That also has tremendous impact.
Potentially. And one of the things when you think about journaling is what you're trying to do is you're trying to make that file system more reliable in some sense, right? You're trying to say, oh, I'll write a journal, and then if my machine dies halfway through a write, I can look at my journal and I can understand what the previous state I was in and reliably rebuild from is. But if you're looking at building a system that's reliable in some sense, that journaling might not necessarily be adding very much to the reliability of your overall system. Someone can still take a saw and go through your server. That server can still die. Your data center can still be flooded in a hurricane or something like that, especially if your data center lives on the east coast of the US, as loads of people who do finance data centers have them there. So you need to have some other way of coping if that machine dies in some sense, or if that disk dies anyway. So there are some situations, I'm not saying do this in all cases, but there are some situations where, for example, it's just better to turn off journaling or something like that.
TMP, for example.
And, what's /TMP?
If you mount your temporary file system, you don't really need journaling because the principle is that's temporary storage.
Yep, that's a perfectly reasonable thing. I'm just pointing out there are some situations in which you might want to ensure that data has reached another relevant external server rather than having to worry about journaling everything on the single disk. That's an alternative approach in that strategy. Okay? I think we're about out of time now, but if anyone has any other questions, I'm happy to talk to you offline. Thank you very much, guys.